Today, we're diving into the really strange world of materials that are kind of having a constant identity crisis. Are they solid? Are they liquid? We're talking about the gummy, bouncy, and frankly bizarre science of polymers.
So get this. It sounds like the setup for a bad joke, right? One of them snaps back. The other just oozes. They seem like total opposites. But they actually share this super weird property that explains everything from the stretch in your tendons to the bounce of silly putty.
So here's our roadmap for today. We're going to start by figuring out this whole solid-liquid thing, then look at how scientists model it with some simple tools. After that, we'll get into some real-world tests, including one from the kitchen, before we wrap up with why any of this matters. Let's do it.
All right, first up, let's tackle this core idea. How can something be a solid and a liquid at the same time? It's this hybrid nature that really gives these materials, which we call polymers, their superpowers.
The fancy word for it is viscoelasticity. But think of it like this. If you slap the surface of water, it feels hard for a split second, right? Almost like a solid. But if you just rest your hand on it, it flows away like a liquid. The material's response depends entirely on time. Time is the secret sauce here.
This breaks down the two extremes perfectly. On one side, you've got the elastic spring. That's your ideal solid. Its molecular bonds stretch, they store that energy perfectly, and then boing, they snap right back. On the other side, you've got viscous honey, our ideal liquid. Its molecules just slide right past each other, turning the energy from your spoon into heat. It never, ever bounces back.
Viscoelastic materials, they live right in that weird middle ground. When you deform them, they store some energy like a solid, but they also lose some energy like a liquid. So they bounce back, but kind of sluggishly, and they flow, but not very well. So how in the world do scientists model this stuff? I mean, it seems super complex. Well, it turns out they use two surprisingly simple things, a spring and something called a dashpot. First, you've got the spring. This is our perfect symbol for pure elasticity. It represents all those orderly molecular bonds stretching. You pull, they stretch instantly. You let go, they snap back, giving you all your energy back. Simple. And then you've got this thing, the dashpot. Just picture a piston moving through a cylinder of thick honey. Trying to push it is hard work because all those liquid molecules have to get out of the way. And all that effort you put in, poof, it's just lost as heat. This is the viscous, energy-wasting part of our material. Now this is where it gets really clever. If you hook them up together, one after the other, in series, you get what's called the Maxwell model. Imagine pulling on this chain. The spring stretches right away, but then the dashpot starts to slowly extend. This is a perfect way to model how a material can relax if you hold it in a stretched position. But what if you arrange them side by side, in parallel? Well, now you've got the Kelvin void model. If you hang a weight on this setup, the dashpot fights the motion, so the spring can't just stretch instantly. Instead, it slowly stretches over time as that syrupy dashpot finally gives way. This perfectly models something called creep, that slow sag you see in materials that are under a constant load for a long time. Okay, so we've got these models. But now, let's see how they actually connect to real-world tests that scientists do in the lab. Because this isn't just theory, it's stuff we can actually measure.
First up, stress relaxation. You can feel this yourself. Grab a rubber band and give it a good stretch. You feel that initial resistance? It's pretty strong. But if you just hold it there, perfectly still, you'll notice the force you need to keep it stretched gets a little bit easier over time. The material is literally relaxing on the inside as its polymer chains untangle.
And this is exactly how scientists measure it. They give a material a quick, constant stretch and then just hold it. They measure how that internal resistance or stress just fades away. What's happening inside is all those long, tangled polymer chains are slowly uncoiling and sliding past each other, finding a new, more comfortable arrangement. So the flip side of that is creep. This is what happens when you put a constant weight on something. The best example is an old bookshelf that's been holding heavy books for years. It starts to sag in the middle, right? The material is slowly deforming, stretching more and more, even though the weight of the books never changed. That's creep. Okay, I know this might all seem a little abstract, springs, dashpots, relaxation, but these exact concepts are used to solve some very practical, and in this case, very tasty problems.
So here's this amazing insight from food scientists. They realized these viscoelastic tests could do more than just give a simple toughness score. They could actually measure the complex texture of meat, not just how hard it is to bite, but how chewy it is, how springy it is, the whole experience.
So, these researchers took on a big problem in the poultry industry called wooden breast. It's a condition that makes chicken breast really hard and unpleasantly tough. Their idea was pretty cool. What if we blast it with high-power ultrasound to break down those tough muscle fibers? And then they'd use our friend, the stress relaxation task, to see if it actually worked.
And whoa, the results were dramatic. Just look at this chart. That tall bar on the left, that's the untreated wooden breast chicken. It took over 3,600 grams of force to compress it. Now look at the bar on the right. After the ultrasound treatment, that hardness just plummeted to about 2,600 grams. A huge difference.
And that's not even the whole story. The treatment slashed the force needed to actually cut the meat by a massive 27%. They basically rescued this tough, woody meat and made it tender again, all by understanding and applying the principles of viscoelasticity.
So, okay, tender chicken is awesome. But what's the big takeaway here? It's that this weird, in-between property of materials isn't just some scientific curiosity. It is everywhere, and it is incredibly important. I mean, this science is fundamental to the world we've built. Think about a car bumper. You want it to absorb the energy of an impact, not just shatter. That's viscoelasticity at work. Or the memory foam in your pillow that conforms to your head and then slowly bounces back. Yep, that's viscoelasticity too. It's an absolutely crucial principle for engineering the things we use every single day.
So now I want you to think about it. The next time you stretch pizza dough or bounce on a yoga mat or squish a gummy bear, you'll know what's going on. You're interacting with one of these fascinating materials, something that's never quite a solid and never quite a liquid, but always something wonderfully weird in between.